Hello everyone, today we'll be talking about a physics problem, and first I'm going to set up the question. So we're looking at a binary star system consisting of two stars, S1 and S2, that have corresponding masses M1 and M2, and they orbit at different distances from a common centre of mass. Both the stars have the same period of orbit around this centre of mass, point C. And these are the variables that we'll be using. So question A first asks us, using the variables that we've been given, to write an expression for the gravitational force F acting on both the stars. So first of all, we're thinking the gravitational force between the two stars will be described by Newton's law of gravitation, which we can write down immediately. So F is equal to the gravitational constant and m1 times m2 divided by the radius between the two. So the radius between the two stars here is the distance from S1 to S2, given by r, and we can see that that's r1 plus r2. So our r here is capital R1 plus capital R2. So the gravitational force acting between the two will be given by G m1 m2 divided by r1 plus r2 squared. So that's our first question there. Question A, part 2, asks us to write down the centripetal force acting on the star S1. So these orbits are circular orbits, so we're thinking circular motion to begin with. So the centripetal force for a body in a circular orbit or moving in a circle is given by F is equal to the mass of the body multiplied by the angular frequency and multiplied by its radius from its point, its center of its orbit. So omega here is given by 2 pi divided by the time period, and we have omega squared. So omega squared is equal to 4 pi squared divided by tau squared. Our n here is m1, since we're looking at the star S1, and its radius from C, r, is given by r1. So if we substitute those values in, we get 4 pi squared, m1, r1, divided by tau squared. So that's the centripetal force acting on S1. Okay, so that's part A. Part B then asks us to use our previous answer, part 2, to write the ratio of the masses of the stars. So what we're going to do is we know that the centripetal force acting on S1 is going to be equal to the centripetal force acting on S2, since they're both equal to F, the gravitational force. So what we can say is that the centripetal force C1, the centripetal force of star 1 is equal to the centripetal force of star 2, which is equal to the gravitational force. And all we need to do then is write that's F1. We need to look at this equation for star 1 and star 2 and take the ratio of those. So if you write FC1 divided by FC2, that's going to be equal to 1. Now, if we substitute in the values for FC1 and FC2, we can see that this factor, 4 pi squared and tau squared, is common to both. So when we take the ratio, this factor will drop out. So we're left with m1 r1 divided by n2 r2 is equal to 1. And then we're looking for the ratio of the masses, which is m1 divided by n2. So we're going to divide both sides by r1 and times both sides by r2, and end up with m1 divided by n2 with r2 divided by r1. And that's the answer for part B there. So then we move on to part C. Here we're given that the ratio of the mass is m1 divided by n2 is equal to 3. Okay, and we're asked to, and we're given the separation of the stars in terms of in terms of a quantity. So R1 plus R2 is equal to 4 times 10 to the 8, 4.8 times 10 to the 12, sorry, meters. Okay, and we're asked to work out the distances from the centre of mass point. So what we wanted to work out here is R1 as a value and R2 as a value. So from our previous question, we can see that M1 divided by M2 is equal to R2 divided by R1. So let's sub that in here. So M1 divided by M2 is equal to R2 divided by R1, and that's equal to 3. So this gives us a constraint on the radius, on the radii. So R2 is equal to 3 times R1. Now we've got two equations and two unknowns, so we can solve for R1 and R2. So if we substitute our value for R2 into this equation here, we get R1 plus 3R1 is equal to 4.8 times 10 to the 12 meters. And now we can solve for R1. So collecting those, that gives us 4R1, then dividing by 4 gives us a quarter times 4.8 times 10 to 12 meters, which is equal to 1.2 times 10 to 12 meters. So we have a value for R1. Now all we do to find R2 is simply substitute this back into this equation, and we can rearrange to find R2. So we get 4.8 times 10 to the 12. So R2 is equal to 3.6 times 10 to the 12 meters. So we have our value for R1 and our value for R2. Now the last question then, it gives us the orbital period of the stars, and it asks us to calculate the orbital speed of S1. So the orbital speed of S1, we know, as we said earlier, that S1 moves in a circular orbit, so we're thinking circular motion equations again, and we're given tau. So tau, the orbital period, is equal to 4 years. This is part C. And we need to work out the velocity of S1. So we know from circular motion that V is equal to omega times R. And we know that omega is equal to 2 pi over the orbital period. And we know the radius, so if we're working at S1, so I need to note this properly. R1, yes. So from knowing tau, we know omega 1, and we've worked out R1 from the previous question, so this is simply a matter of substituting in some values. So you have 2 pi times 1.2 times 10 to the 12 divided by 4 years, but we need to work in SI units. So our SI unit for time is the second, so we need to convert 4 years into seconds. So multiply by 365, that's the days in a year, multiplied by the hours in a day, and then minutes and seconds. There you go. So substituting our answer in and putting it into a calculator gives us out 6.0 times 10 to the 4 meters per second, and that's the two significant figures. And that's the end of that question.